All right, welcome to the Explainer. Today, we are tackling a question that, as one Reddit user so perfectly put it, just makes your brain hurt. We're going to dive into why our universe started in this incredibly tidy, orderly state, which in turn created a one-way street for time.
I mean, think about it. You see a fire melting an ice block, and it looks totally normal. Dye mixes into a glass of water, no problem. But if you try to play a video of those things in reverse, an ice block magically forming out of a puddle, it just looks wrong. Impossible even. Physicists have a name for this one-way street, the arrow of time.
And here's where things get really weird. Almost all the fundamental laws of physics we know, things like gravity, electromagnetism, they honestly don't care about the direction of time. They're what's called time symmetric. A video of planets orbiting the sun would look just as plausible forwards as it would backwards. But there is one huge exception to the rule: the second law of thermodynamics. It's the only fundamental law that seems to know the difference between the past and the future.
So our prime suspect for why time has a direction is this incredibly powerful idea called entropy. Now, you've probably heard it described as a measure of disorder, or just plain old messiness.
But messiness is really just a shorthand. A better way to think about entropy is to ask, how many different ways can you arrange the bits and pieces of a system to get the same overall picture? A state with high entropy has tons and tons of possible arrangements, which makes it statistically, super likely. A low entropy state, it only has a few possible arrangements, making it incredibly rare.
Think of it like this. There is only one single way for all 693 pages of the book War and Peace to be in the correct order. But there's a truly staggering number of ways for those pages to be out of order. So systems naturally drift towards the state with the most possibilities, what we call the most typical state. It's not some kind of magic, it's just pure probability.
And that's the crucial point. The second law of thermodynamics isn't just a suggestion, it's pretty much a statistical certainty. For any closed system, and you can think of the entire universe as a closed system, the total entropy, that total typicalness, will always go up over time. This is the engine that is constantly driving the arrow of time forward.
Okay, so this all seems pretty straightforward, right? The universe is getting messier, and that's why time only moves forward. But if we try to rewind the cosmic clock, this simple idea leads us to a really shocking twist, and it involves the most powerful force in the cosmos: gravity.
And boom, here's the paradox. Our best models of cosmology tell us that the early universe was this incredibly smooth, uniform, hot soup of particles. Now, intuitively, a smooth gas sounds pretty messy and disordered, right? It sounds like a high entropy state. And you know what? If you could ignore gravity, you'd be absolutely right. But in our universe, you can never, ever ignore gravity.
See, gravity completely flips our intuition on its head. In a universe where gravity is in charge, a smooth, uniform cloud of gas is actually a state of incredibly low entropy. Why? Because it's a very unstable and statistically unlikely setup. Gravity wants to pull things together. The most probable, most typical high entropy state for a system with gravity is for all that matter to be clumped together. It's kind of like trying to balance a pencil on its tip. That smooth, balanced state is just waiting to collapse. So the messy, disordered future of our universe isn't some uniform gas. No, it's a lumpy cosmos, full of stars, galaxies, and eventually giant black holes. This whole new way of looking at entropy forces us to see the beginning of our universe in a completely different light. And it reveals one of the absolute biggest puzzles in all of physics.
The logic here is just inescapable. If entropy always increases, and our universe today is clumpy and high entropy, then as we rewind the clock, the universe must get smoother, and therefore lower and lower in entropy. And this leads to one startling conclusion. The Big Bang itself must have been the most ordered, lowest entropy state in the entire history of the cosmos.
Now, this isn't just some casual observation. It's such a foundational idea in cosmology that it has its own name, the past hypothesis. It's this core idea that our universe had a very, very special, finely tuned beginning.
So, we've finally arrived at the ultimate mystery. Every statistical law we know screams that the universe should have started in a typical high-entropy state, most likely as a giant black hole. But instead, it began in this 1 in a trillion, super smooth, incredibly orderly configuration. The question is, why?
So how are scientists trying to solve this epic why? Well, there's no single accepted answer yet.
but the investigation is pushing us to the absolute frontiers of theoretical physics.
I mean, the proposed solutions are just fascinating. Some theories point to something called cosmic inflation, which is this idea that the universe went through a period of insane exponential growth right at the start, stretching everything out until it was perfectly smooth. Others imagine cyclical models, where universes are born from the ashes of old ones. And then you get the really mind-bending stuff, like the idea that our entire universe might just be the inside of a black hole, or that we need a whole new theory of quantum gravity to even ask the right questions.
You know, as we grapple with these immense concepts, it's probably worth remembering this very humbling thought. The questions we're asking are just so profound, and the answers might actually lie beyond the limits of our own intuition, an intuition that, let's be honest, was built for a much, much different scale of reality.
So why does any of this really matter? Because that one special low-entropy moment at the dawn of time is the ultimate reason for everything that came after it. It's the reason stars had the fuel to form, it's the reason planets could come together, and it's the reason there's enough order in the universe for complexity and even life itself to exist. In a very real way, we are all children of that one improbable, tidy moment.
And that leaves us with one final lingering question. The arrow of time was shot from a very specific, finely tuned bow. Understanding where it came from isn't just about understanding our past, it's about understanding the very nature of time itself, and maybe, just maybe, figuring out where that arrow is ultimately heading.